seems to work.
Okay.
We're confused. Okay.
Anyway.
Now we're on find replace path. Okay.
Yes.
But now I'd have to do this packlet install. Is that correct?
Yeah.
Okay. Okay, now what is here? Gosh, what is all this stuff?
Well, we were just working in it. So these,
I was trying to explain, James, how it works.
well, what you have in mind for getting from find replace path to a reverse find equational proof graph, which we're still thinking through. But let's just start with how find replace path itself works, Nick.
Well, should we do it for strings or should we do it for what should we do it for?
Well, just any easy one from axiom theory. Like, I'm pretty sure any notable theorem from Boolean axioms works because I tested it on at the end. So we can basically derive any.
Okay, let me make a let me start this off again. Okay, so you say find replace path, and then you say, so can you give axioms in the?
Yeah, you can. It takes the same arguments as find equational proof. Exactly the same.
That wasn't my conception of find replace path. Now, what I was imagining for find replace path is really directly transformation rules. You see what I'm saying?
That's what it is. That's what it is.
Okay, but so I could give, I could just give something that says f of x blank. Didn't I have a version of find replace path long ago where I have some examples?
Well, I've seen like a few versions from Mano and row one, right?
Okay, so I think the one that turned into Mano's version was my version.
Maybe. I put them all into archives for now in a separate folder. All the definitions I found.
So I just want to remember what I was talking about there.
I think you were talking about that you just start basically future and past entailment cone derivation from your axioms and your hypothesis and try to merge them somewhere in the middle. Which you can imagine is pretty damn hard to actually prove something. If you have many steps in between.
Right. Okay, so here we go. So this is a version of my find replace path generating a multi-way fragment. So do you have this notion of a multi-way fragment?
No, I don't. I just have. It's not gonna look like that. It's like it's a little bit different. Maybe I'll do something similar to that later.
Okay.
But for now, you just provide the same arguments as find equational proof, but you have when you have equalities, right? So your rules are equalities. Potentially, you just can make one-way rules using implication.
Okay, but I do believe that the functionality that I had here is kind of important. That is, I mean, so maybe the algorithm that you're now using is a much better way to do this, but I don't know what you're now doing.
Well, let's take an example.
Okay, but roughly, Nick, what is the procedure that you're using?
I'm using cut elimination, as you said during the stream.
Mhm.
You take the proof from find equational proof. You take the proof graph or proof data set and
Mhm.
just reverse engineer every lemma to make it into just a path from left hand side to the right hand side, replacement path. That
But it doesn't.
does
It doesn't.
just
Yeah.
one single rewrite.
Yeah. Right. It doesn't
You do
branch.
it.
Yeah.
Yeah, you do it recursively for each lemma until you just arrive at this replacement from A to A. What is your conclusion is. And somewhere in the middle you have a hypothesis, so you just can reverse this path however you want. Then
Okay, well, that's
and
nice.
make it.
That's beautiful.
Yeah.
I mean, that's very nice. And so that's leveraging the technology of find equational proof to do this, basically.
Right.
Okay, that's lovely. I mean, I still think this isn't completely stupid what I had here. Actually,
Okay.
I'm going to
Let's.
clean this up, but I'm trying to remember what, because the whole point is for the general multi-computation problem, this notion of you know, this is like a temporary assignment. It's trying to get to, why is this, wait a minute. Oh, I see, it goes to there. It's confusing. You know, this is like sort of this is a version of multi-computation in which you're stating both the input and the output. I mean, there are many versions of multi-computation, but this is one of them.
I see.
Where you're giving essentially temporary assignments. You know, usually in a computation, you just give the input. And then you say, run me to a fixed point.
Sure.
But this is doing something, it's doing something different. This is more like a proof, but it's in an infinite computation. It's doing kind of a different thing. And so another thing you might do is to say, in this environment, start from this.
Right.
And so by the way, what we're quoting here, like multi-way fragment, this is exactly, you know, the observer question.
Go on.
Well, it's like, what do you want from this thing?
Yeah. Okay. Okay. I see. Yeah.
And you know, and then the other cases here, things like you don't know the destination. You know, the standard computation is find replace path with those rules, and then the destination is just a fixed point, right? And you can give the destination, you can give a fixed point, you can say go to the fixed point, you can say find, you know, you could have all kinds of criteria for what the destination should be. And in the case of, you know, you can have a pattern destination, I suppose. In a sense, one pattern, yeah, it's interesting that these are meta patterns that you really want here. I mean, I just want to make a note of this concept. I mean, that right. So it's just it's I mean, you could say find replace path of rules, comma, init, comma, and then you could either say destination, or you could say the meta pattern fixed point, you know, whatever it is, fixed point, that's where or you could say, I want the or I could get multiple destinations, etc. Okay, now I'm going to pay attention to the next version. Although I'm not convinced that it's the same function really. Okay, so now what do I do with yours? So you say I can say axiomatic theory of some random axiom.
Don't try this one. This is annoying a little bit. It's Boolean axiom work.
Okay, all right. Okay, so now, oops. So now you say I do notable theorems.
Mhm.
Okay. So let's try the law of absorption, this one here.
You can use names because find equational proof also just allows names.
Okay, so what do I say? I say find replace path.
Mhm.
Then name of your theorem.
First.
Absorption.
Yeah. Then Boolean axioms.
That it?
Yeah.
Oof.
Damn.
Is that because I did the wrong thing with the packlets and so on?
Let me just to be sure. Find replace path absorption. It works for me.
Okay. Well, maybe I need to uninstall the packlet. Source version.
Maybe I well wait, let me reupload it really quick. Maybe I just had an older version. But for that.
The packlet or the Codo one?
No, Codo 1 is not used here. The packlet.
Yeah.
Try again. The packlet install.
Humph. Okay. You're doing exactly the same thing, right? Well,
Yeah.
let me. Oh, but no, wait a minute. I didn't reload this. I need to reload this.
Sure.
But that is not a good sign.
Oh, because you, I don't know.
Okay, let me quit the kernel. Okay, now let me load this.
Good.
Aha. Much better. Okay. Now, what on earth is this?
So there's a bunch of properties, but I guess you want just path. Property path.
At the bottom.
Okay.
Yeah.
Okay. So is this a pure substitution path?
Yeah, you can even like among the properties, you have this rewrite sequence. How do they call it? Basically, a list of actual functions that you just apply step by step to the left-hand side. And they all contain just replacements. And some novelty generation when you can replace the variable with something.
With what? What can you do?
You can replace variable with some new term like that. It may be just a renaming or just maybe more complicated.
Okay, but so in terms of our token event graphs, this will be just a linear token event graph. Is that true?
Right.
Yeah, single path, non-branched.
So when I talk about in this picture, what we'll see here is just, I mean, if I do this right now.
Yeah.
I probably just do this, right? Find replace path.
Yeah.
Okay, so let's say that thing path. Q.p. I don't understand. Why isn't this?
So
Why isn't this
somehow it's
equation?
in another direction.
What's that?
It's in another direction for some reason. Or just how find equational proof, I guess. Decided to find to make it.
No, but why isn't this a series of equations? Why is this expressions, not equations?
Oh. Well, that's the point. You just
What
have terms. You prove the equality of your left-hand side and your right-hand side.
Okay, but that's nice. But that's not what we were doing. I mean, okay. So that's one way to do this, but using, so we're always applying this axiom.
Mhm.
And we're doing it
In different
that's like the-
orientations and different positions.
yeah, right. So that's like the first way that I show it being done in NKS, basically.
Right. Yeah.
As opposed to the way that, okay. But as we think about kind of the development of mathematics, we're thinking about not eliminating cuts. And we're thinking about building up intermediate lemmas.
Mhm.
Yep.
In this kind of way, more or less.
Yeah.
So this is the case. Okay, so what you've done here is you've got something which, and this is very nice, goes kind of all the way. What
Yeah,
does happen? Yeah.
And next, I want to make inverse of that, because
that
I
mean?
think working with paths like that and sequences is much easier than branching graphs.
So
Right?
the
So
idea is,
I think that's
yeah.
the point. It's not to reverse, for example, if you want a hypothesis instead of your conclusion at the bottom of your graph. I think it's the way to go is just to make a path like that, rotate it, and go backwards. Introduce more lemmas again.
Yeah, that's it. Right.
What do you mean?
We take this path, which is unbranched, we reverse it, and then you introduce the lemmas again to get the branched reverse graph. That's the point. Right, Nick?
Yeah, that's what I want to try to do next.
Okay, so hold on. And the point of that is, So this one is what you get without lemmas. Is that the idea?
Yeah, it just has axioms.
And what happens with my Boolean algebra axiom?
So it works the same way. It's just I still have some bugs to walk around, and this huge axiom somehow causing troubles.
What's the
Kill
bug? Do you know?
Well, there's a lot of bugs. It's like I did report like several for the find equation proof
Yes.
that that makes the life very complicated.
What kind of bugs are they?
It's like there's like orientation is incorrect or position is just incorrect. You have to deduce it. Like I have workarounds for some of them. Like when the position is just incorrect for the substitution lemma, I just try to find the subterm where actually substitution happens. Right? It's annoying. Sometimes it's just like some Waldmeister guts somewhere spilled over in the inside of data set. So we can't recover any information from there. So we have to deduce it again. So basically, yeah.
But there's
So for now,
another
it's just a lot of hacks.
but there's another problem with the verification in terms of the co-substitution or the critical pair lemmas. Basically, it doesn't actually verify them. Right, Nick? This is the other issue with find equational proof.
Yeah, there's like no easy way to recover variables. That's what I think happening for this guy, because there's a lot of variables. Maybe like there's some I don't know, naming troubles happening. Yeah, find equational proof is it's kind of very experimental currently. It's like I wouldn't trust its proof actually.
Really? Well, you wouldn't trust the proof. I mean, the fact that there is a proof seems fairly simple.
The output of Waldmeister I can trust, but what happened after that as a post processing, with like deriving the data set and all the information and the proof function is not trusted at all.
Okay.
There's a lot of bugs in there.
Do you understand how it works inside enough to be able to
Not yet, but maybe
okay.
later.
I don't think it's super complicated. I mean, I think it's not super complicated. I think it's
I kind of have an idea. I looked into that a little bit. Like the Waldmeister output, the raw output is just a bunch of like steps in some way. Essentially what you already have, like lemmas and critical pair lemmas. You just have to parse it correctly. And something there is not true, I guess.
right.
No, it's not going to work. It's like Wolfram axiom somehow. See, all the messages is what I did in order to debug what actually is going on. It's like
Okay.
it's not the bug in my code. It's like the position is simply incorrect.
Okay.
Something like that.
But I mean, so look, there are different things here. One is what I'm trying to do for this blog. Another is the path forward, so to speak, for find replace path and for multi-computation in general. For this blog, you know, what I'm trying to show is how a fragment, I mean, this is the kind of thing I'm trying to show, right? It's showing how we can get from these accumulative token event graphs to proofs using lemmas. But the point is that there's much bigger ones that you can get by using the internal mechanism. Is that a fair statement?
Yeah, basically using this non-failing completion. You can have much bigger proofs.
Right,
That is like you have no chance of doing just don't comment them on the intersection finder.
right. I mean, look, the other thing that should be done with find equational proof is this business about how if it's spent too long, it should try and find a counterexample.
Yeah, that's
Okay. So look, I mean, this business about how it evolves to a tautology, is that essential or is that just a feature of some innards of theorem proving?
I don't know. Maybe that's how it was stated. Maybe this is much easier to derive it this way.
No, I understand, but I mean, I'm asking in terms of the proof that we want.
Right.
Is not this proof graph. The proof we want is from the axiom derive the statement. Right?
Yeah. And for the sequence path, for the sequence proof, it's easy to do to derive it.
Sorry, what do you mean? For the path where A equals B, so to speak, and you're making the path from A to B.
From A to A, right? The conclusion is some kind of A to A path with the hypothesis in the middle. Then you just rotate it, and you'll get the path from left-hand side to the right-hand side of your hypothesis.
I see what you're
and
saying.
you can do it like for any lemma or any tokens in the proof graph.
Okay, so your claim is that somewhere in the graph, you start from A and you derive A again.
Yeah.
And that somewhere in the middle, you generate everything.
Yeah, what was there in the proof graph, basically.
Okay. But to me, the clearer thing, let's see, if you're doing something equational, but if you're doing something predicates, this is not, you can't do a path like this, right? If you're doing something with an existential quantifier and things, you can't do this.
Probably, why not? So if find equational proof can do it, then I can do it too.
Yeah, but I don't think you can state it as a path like this, can you? Because it's not, unless you simply state it as a path going from the hypothesis to, well, no, this is going from the axiom. No, this is going from this side to this side using the axiom.
Yes.
So what you would do is you would go from the predicate to a tautology. Is that correct? That's what you would do in a path version of proving a predicate.
Well, find equational proof is always turning your predicates into equations anyway. So it's going to be just
I know.
some version of the predicate, equational version of the predicate that you can rewrite. I guess in the case of predicate, you always rewrite your predicate into this A or not A thing. That's what it does.
Yeah.
That's how it's going to look like.
Okay, look. Again, okay. Well, I mean, okay, let's look at the flow of what I'm trying to write. And then let's look at the whole point here is to describe, right. So for this multi-computation thing, it is very much assume a fixed set of rules Okay, so the generic form of multi-computation, assume a fixed set of rules, then try and go from one expression to some either defined or undefined endpoint.
Mhm.
And there's a kind of a pure discovery version. Okay, so this is more on the multi-computation side. So, okay, so you've got rules. The rules that you have are somewhat equational. The general case that I was looking at here, which might be equivalent, I don't know. Is it equivalent? Pattern variables. I mean, in general, this can be an arbitrary computation.
Well,
I mean,
you just turn rules into implications and just crank your logic again.
yeah, I understand that. For replacements, I think that's correct. For let's see, it's essentially a find computation. Well, okay, in general, all right, look. So, I mean, this is, let's see, do I have a multi-computation section here? So I've got rules, I've got init, and then I've got some form of destination. And then I've got, what to show. So the destination, destination can be specific expression. That's what you're considering here. It could be the meta expression fixed point. Could be a pattern for expressions, which would give you a whole bunch of expressions as output.
Yeah, if you find equational proof, we're actually finding different kind of proofs, then that would also work.
What do you mean?
Because like if you specify a pattern, you're essentially specifying some kind of existential quantifier, right?
Yes, that's like an existential quantifier.
So you just crank the find equational proof with existential quantifier. It's just not constructive in general, I guess. That's the point.
Well, no, but what you want to do is you want to actually give a bunch of those. I mean, we want to actually enumerate lots of, have the actual expressions, like be able to generate 1,000 of them or something. And then the what is things like Simply test if it's possible. Give a path. Give multiple paths.
I wonder where it's actually when there's an existential quantifier. If you turn it into a replace path, is it a matter of just then enumerating over all the scaling functions that you produce along the way?
All the
Like
which?
you have this, it's like you have like a writing path. You know that like you have. Then you have, for example, if it was a predicate, you have a writing path from this predicate to some true
Yes.
statement. And if it was an existential quantifier, there is going to be some calling functions in between.
Yes.
So
Yes.
you have this path with calling functions. Then you having this path, you just enumerate all of them and check maybe whether it's still true. But I guess it's still all going to
Probably. I mean, I don't know if that's really right, because I think that's like saying that you have a constant of integration or something, which can have arbitrary values.
Yeah.
I'm not certain if that's right for well, okay, worth understanding. I don't really know. But essentially what we're saying here, I mean, what's a little frustrating, and you've got a version of it here, right? Is, or you've got the replace. You've got a rule, which could probably be one way without harm, but, or you've got multiple rules there, and you're saying, I mean, it is true, isn't it, that replace, how do we do, oh, replace part. And does replace part have an operator form?
Yeah.
But really what we want actually is map at of a particular rule. Am I wrong? It's kind of a replace at, isn't it? I mean,
yeah, it is always a replace at.
yeah, but there isn't a replace at function.
Yeah, only in the resource function repository.
Okay, but so what we'd want is something where we have the rule and the position and a curried replace at effectively. So that this is applied to an expression. And so what we're saying then is the proof is a composition of replace ats. Is that correct?
Yeah. That's what that list of replaces is. Map at replaces like replace at.
Yeah.
And replace all contains this novelty generation. I guess you can get around that.
Okay, so this is basically exactly the thing, except that in principle, we could state it as a single composition, which you could then take apart if you wanted to, if I'm right. Right, that, and then that composition would explode. If you gave it the left-hand side, it would just generate the right-hand side. Is that correct?
Mm-hmm.
That's like the test what I do in the is checking. Like rewrite test with success, then actually what that list of replace functions, if I just run it on the left-hand side. it reproduces the whole path.
Right. If you run them as if you do a nest list or some kind of fold
Fold.
list of these.
Yeah, I'm doing fold list. Yeah.
Okay. I need to understand novelty generation. I need to understand what that is. I mean, I understand what it is nominally here. I mean, it's part of the canonicalization of variables, but does it matter?
Well, matter in what sense?
Well, I mean,
It doesn't
you have
matter
to
if you
do it.
want.
Yeah, go ahead.
It doesn't matter if you actually want just one way rewriting rule. But actually, proofs are usually stated as just a sequence of terms when rules can go both directions. So if you actually want to rewrite, you have to generate a novelty. But if you just look at it from other way around, it's just there's some reduction happens instead. But you just have no way to go into that term if you start from just left hand side, right? It just came from nowhere.
I think I understand. I think I need a simpler example, but okay. So look, we've got two different things going on here. We've got the bigger picture of creating. See, I just want to say that I think there is one version of this that works with rules, with pattern matching.
Mm.
And there's another version which is just of a function here, where the only thing it has is at various stages in it, it has this thing called multi. And every time you generate a multi,
Yes.
that is producing a bunch of new paths.
Okay.
And so that's the general case of, that's like a multi-way system function. That's what, and then this is a particular case where you're finding a path. And I don't know how general this can be. I mean, I think that requires, if you've got arithmetic going on here, this isn't going to work, right?
So if you
Right.
have just equality axioms, it works the same way.
What do you mean? I don't understand. If I've got a function here and I'm trying to find which branches from that function cause you to go from the init to the destination.
Well, then it's not going to work because it doesn't
No,
branch.
it can't work. What do you mean it doesn't branch? Of course it branches. It branches unbelievably internally. It's just this is finding one particular branch.
That's what I mean. Yeah, that's what I mean.
Right, but the point that I'm making is there's a class of things for which you can do that,
Yes.
which is the class of things for which which can be compiled into equational logic.
Yes.
But like why can't you just turn any one-way rule into an equation? You basically state that it's reversible.
I know, but you can't turn you can't turn the function GCD into an equation, right? If your thing is a multi-way graph where, or divisors, for example, n goes to divisors of n, right? That's not going to.
Then there's not going to be any algorithm that simplifies the problem. You're just going to it just turns into a search problem.
I'm not sure that that's true. I mean, yes, in a first approximation, that's correct. And that's exactly what my original function before it was rewritten by multiple people did, was it tried to do I guess there's one version of that function which is purely forward, but there's another version. Okay, so there's different cases. There's cases where you can invert the function. So you can at least go in the forward and backward codes. And then there are cases where you can do much more compilation. I mean, this is the analog. If this was sort of a neural net, you would do automatic differentiation. Instead, what you need, what is the analog of automatic differentiation for this problem?
You need ordering. It's like what Knut-Bendix completion. It's like the search, there is some kind of ordering based on which you can decide which path to take. So if you can specify it, then you turn it. You can improve your search.
Okay, but Knuth Bendix, why does unfailing completion? Let's see, the non-obvious point is that that's possible. Even though, or maybe it's obvious that yeah, I mean, so let's see. You can pick which path. The whole point about completions is, in the end, it doesn't matter which path you took.
Yeah.
I think. But I mean, so the main point that you're making, which is a very good point, is that you believe that it is possible to take our pattern language and enough compile it into equational logic that we can solve this search problem efficiently. Is that a fair statement?
Yep.
What does accept? How does accept work?
So just not. Except is not in logic.
Yeah, fair enough.
Alternatives is a disjunction.
Right. Kind of makes one wonder about the question of whether one could compile patterns into logic. Given a set of patterns, can you compile it into logic and just run it much more efficiently? I think it's something we thought about like 30 years ago and never did.
I have a backwards function that takes first order logic formula, turns it into just a pattern with just rules.
Well, do you think you can reverse it?
So I think
Can you
so.
show that function? That sounds interesting.
Well, it's called unquantified. You should load it. So just give it any first order formula.
Unquantified.
Lowercase. They are all.
With a capital Q?
No, I think you just
Is it in
quantify.
here?
It should be part of mathematics. Wait, let me see. Maybe I forgot to export it. Oh, unquantify formula. Unquantify.
Okay. So what are you saying? So for all A and B,
For all or exists.
or which?
You can,
Yeah, okay. There exists a C such that A equals B dot C. The hell
actually,
is
C
that?
is not C is not a pattern. It's like just a term, but all variables that exist universally quantified are now pattern.
I don't even understand why that B dot C. Why is it of A blank B blank?
That's how columnization works essentially, because existential quantifiers inside your for all. Your column function should depend on those.
I see. Okay, fine.
Yeah, that's essentially escalation.
So you claim the other way around would also work, that we could essentially compile patterns. That's very interesting. I mean, is that of practical use if we had a whole collection of patterns what would we do with it? We would whole collection of patterns. Wait a minute. So this would give us, we could turn axioms, we could turn pattern matching rules into axioms, basically.
Yeah.
Well, it's very interesting. Okay, so then match Q becomes this, match Q is essentially, can you find a path from here to there?
Yeah, match Q is like, it's an instance. I even
Right.
have it in my dictionary. It's like term instance.
Where is your dictionary? Well, okay, look, this is highly interesting and really important, actually, for the whole multi-computation story. I hadn't really considered this possibility. There's a different set of functions. I guess maybe that's what find replace path was, between the pattern case and the general function case. Maybe I had considered that. Maybe it's obvious. Okay. Okay, so look, just trying to break down what we have to do. So there's a set of things that are needed for this post, and then there are a set of things needed for general multi-computation. They're somewhat different.
Yeah.
But for the post, we're trying to explain how this relates to automated theorem proving. It sounds like we're going to have a very good story there, but that's only, honestly, it's just the tip of some giant iceberg of interesting stuff. I just want to be able to say, because I've been confused about this for years, what the relationship is between kind of the substitutions in a token event graph and what happens in theorem proving. But hopefully we'll be able to explain that. And then okay, that meanwhile there are other things which, I mean, I don't know what the plans are for the next little while, but there are other things in here. There are just many, many, many details of things that weren't worked out. And I think it is somewhat likely that in the next few, I don't know, days-ish, I will finish a complete pass of writing this thing, but with many holes, with many pieces that have to be filled in. And it's and I just hope that the things that are filled in don't change the main narrative. So another thing I really wanted to do was to study this axiom systems in the wild, which is just start with an arbitrary axiom system and see what it does. And I think we're in a position to do that now. We've got both, if I'm not mistaken. Okay, so hold on. What we can do there. Yeah, that the thing from NKS where we're looking at what theorems are true for a given axiom system. Is something we can, okay, so here we can say, what is the token event graph structure, e.g. its dimension, and then where does, by the way, I don't want to interfere with everybody's Christmas Eve. Oh,
it's not even the eve for Nick, is it?
No. What is
well,
Christmas?
Merry Christmas. Oh dear. Well, I don't want to listen. Please don't. Don't let me. I mean, really, it's not. It's
Steve, I could probably meet for like another 20 minutes if you want to continue to discuss the draft 4, and then I'll probably
Okay.
have to go.
Okay, that's fine. And please, it's all. I mean, I don't need to. My writing is going fine. I'm just there. What I wanted to do here was to get kind of a checkpoint on. I mean, okay. Where in meta-mathematical space does a given axiom system reach? So in other words, what's the shape of the axiom system? If we lay out all possible axioms,
Yes.
what is the shape of this axiom system in mathematical space? And for this, I think I have what I need. I mean, I think all I need, if I'm not mistaken, is this thing here, right? I need this function that, is this right? Token event substitution graph, is that what I need? I can't even remember anymore. I'm trying to figure out which theorems are derivable. How big is the token event graph, and which theorems are derivable? I think I should let you guys do your Christmas, and I should go back to my writing. And I apologize for impinging on
Don't worry.
No, it's okay. I was celebrating in the morning, and I'll continue to celebrate this evening. Do you have plans, by the way, Stephen?
I think so. I mean,
Okay.
I mean,
Did you ask your daughter to write a letter to the Ruliat, by the way, this year?
what do you mean?
Well, you request all the computations